All right, IBAI SL2. We've come to the last section in Chapter 7. It's our final probability day, and today we're talking about normal distributions. Now, we've been doing a lot with binomial distributions, doing binom CDF and binom PDF, but today we're going to talk about normal distributions, which are slightly different. Binomial distributions can sometimes be curved to one side or the other, but normal distributions always have a perfect symmetry right down the middle that you could fold it right over. Now, they might look a little more squished or like bunched together based on a standard deviation, but they will always have that horizontal symmetry. The notation that your book is going to use is X apostrophe, not apostrophe, I forget what the symbol's called, and then this is a mu right here. It's a Greek letter, but it stands for the average. And then this sigma is standard deviation. So, just a heads up about what normal distributions look like. If you have a mean, which remember that the mu is the average, it's the mean, it's right in the middle right here. So this is your mean. If you go, with all these problems, they give you the standard deviation along with the mean of the distributions. So each of these bars are a standard deviation away from the mean. So this is 1 standard deviation up from the mean, this is 2 standard deviations up from the mean, or 3 standard deviations up from the mean. You can also go below the mean and say this is 1 standard deviation below the mean, this is 2 standard deviations below the mean, and this is 3 standard deviations below the mean. Now, if something is normally distributed around a mean with a certain standard deviation, that means certain percentages of the data fall within certain standard deviations of the mean. So, like if somebody asked you, like what percentage of the distribution, the normal distribution falls 1 standard distribution below and above the mean, like 1 standard distribution within like a below and above the mean is going to be 34 plus 34%, which is 68%. You don't necessarily need to know these numbers like 34, 13.5, 2.35, and 0.15, because I'm going to show you guys how to find them using your graphing calculator. I just thought you guys should see the visual about what's actually happening. The way I always think of normal distributions is if like I grade a bunch of tests and then the average is like a, like a C right here. And then that means if like the further you move up, that there'll be B's and A's and A pluses. And then the further you move down, there'll be D's and F's and F minuses. So it's like a lot of people fall within this first standard deviation. They're around the mean. But then like the further out you get, like the less people are there. So the people that got B's and A's are probably similar to the people that got F's and D's. And then, as you move really far out, like only a few people got F minuses and got A pluses, sort of thing. So like it's got this nice normal bell curve to it. We are going to be using normal CDF for the majority of our work. This is still in the distor menu. So you're going to hit second and then vars. And then it's one of the first ones up at the top of the menu, normal CDF. Now, the way normal CDF works is that you're going to put in a lower limit, an upper limit, the mean, and the standard deviation. Sometimes they'll ask you, like, what's the probability that something is less than 27? So that means if it's less than 27, it's from 27 all the way down to negative infinity. But your calculator does not have a button for infinity. So the way you trick it into doing negative infinity is negative 1e to the 99th. This means negative 1 times 10 to the 99th. So it's like a negative 1 with 99 zeros after it. So that's how you trick it into thinking it's a negative infinity, because you just do a absurdly large negative number. Same thing with positive infinity. Sometimes you got to swap in the 1e to the 99 on your calculator. All right, let's do some problems. Let's say capital T is the waiting time when you call customer service at a company. So here they're giving us that the average wait time is 19 minutes with a standard deviation, or maybe these are seconds. I think these are seconds. So average wait time is 19 seconds with a standard deviation of 1.3 seconds. Find the probability of t less than 17. So this is the probability that you would wait less than 17 seconds on the phone for customer service. The way you're going to do this is go to your distributions and use normalcdf. So this is going to be normalcdf, negative infinity, all the way up to 17. And then the mean is 19, and the standard deviation is 1.3. When you do that, I think it's about 0.062. Now, the probability that the wait time is less than 21 is still going to be a normal CDF problem. So then the mean, or no, all the way up to 21 on that one. And then the mean is 19, and the standard deviation is 1.3. This one, oh wait, sorry, the book is being weird about this one. Let's just crunch it out. Oh no, wait, it's 0.938? Yeah, I believe. So normal CDF, I'll check it. -1, second E, 99, comma 21, comma 19, comma 1.3. Oh my gosh, I did it wrong. Sorry guys. -1, second E, 99, all the way up to 21. Average. So I should mention that if you're rocking like an 84 plus silver edition, that you get a nice menu for this. You don't have to punch it all in. But if you're on like an 83, you do have to punch it all in. So this is about 94.94. So that means like 94% of the people calling, their wait time is less than 21 seconds. But like less than 17 seconds is like 6%, as opposed to 94% here. Now, this next one, probability that wait time is over 20.3. That's from 20.3 up to positive infinity. So this will be normal CDF. Starts at 20.3, goes up to positive infinity. Average is 19. Standard deviation is 1.3. 0.16. Now, this last part here says the expected number of times the wait is less than 21 seconds in a sample of 107 callers. So we already found the probability of it being less than 21 seconds. That's right here. It's 0.94. Now, if there's going to be 107 callers, you really just need to multiply that 107 times 0.94. So about 100 callers, maybe 101 if you're rounding up, but I guess we should round down. So that means 100 callers wait less than 21 seconds out of the 107. Next problem. The lengths of trouts in a fish farm are normally distributed with the mean 39 centimeters and a standard deviation of 6.1. Remember, they should always give you those things with a normal distribution. Find the probability the fish is less than 35 centimeters. You would use normal CDF for that. I'm just going to say that we're just going to write probability of L is less than 35. using your GDC is going to be 0.256. So use normal CDF for that. Someone catches 5 fish. Find the probability that at least 2 of the trout are more than 5 centimeters long, 35 centimeters long. Well, first up, we already found the probability that a fish is less than 35 centimeters is this. So that means the probability that a fish is more would be that taken away from 1. So 1 minus 0.256 is 0.744. That a fish is more than 35. Now, someone catches 5 fish, find the probability that at least 2 of the trout are more than 35 centimeters long. This is definitely a binomial problem because of the whole at least 2 of the 5, because there's so many different ways to catch 2 fish out of the 5 that are bigger than 35 centimeters long. So we are going to do a binom PDF. Nope, CDF. At least 2. Oh, so because binom CDF works from left to right, we're going to have to do 1 minus binom CDF of 5 fish. The probability that they're over 35 is 0.744. And we want to go the other way from at least 2. So that would be just going up to 1. And I believe when you crunch that out, you get 0.983. Let me confirm. Yeah, 0.983. The next part says, find the probability that a fish is longer than 42 centimeters, given that it is longer than 40. So we need to find probability that L is bigger than 42, given that L is bigger than 40. So from the equation, the given equation, this would be probability of, well, you have to do the intersection of 40 and 42 on the top, but the intersection of 40 and 42, more than 40 and more than 42, is just the probability of the fish being over 42. And that's going to be divided by the probability that the fish is over 40. So with each of these, the top and the bottom, horrible arrows, these are each going to be normal CDFs. From 42 up to infinity and 40 up to infinity. I think if you crunch both those numbers, I guess I could crunch them. Normal CDF, 42 to infinity. Standard deviation was 39, and average was 39, and standard deviation was 6.1. So the top is 0.311, and the bottom is going up from 40, 0.435. So if we take 0.3111 and divide by 0.435, 7.15. Sorry, 0.715. Can't talk today. So that's the probability that a fish is longer than 42, given that it's already over 40. Last part, determine if events L being bigger than 42 and L being bigger than 40 are independent. There's 2 ways to show that things are independent. One of them is that the intersection of A and B is just the probability of A times the probability of B. The other way of doing that is saying that the probability of A and B is equal to just A. I think they mean probability of A. So, because this is 0.715 and the probability of just getting their intersection is 0.311, these are not independent. So since because those numbers aren't the same number, the events are not independent. One last problem. The weights of cauliflowers are normally distributed normally, nice, with the mean 821 grams, so that's necessary information. The mean is 821, and the standard deviation is 40. The heaviest 8% need to be repackaged. Find the weights of the heaviest 8%. So what's happening with this problem is that there's some distribution of cauliflowers, and then somewhere up here at the top, there's a cutoff line where this area right here is 8% of the curve. Now, normal CDF, you punch in a mean and a standard deviation and a score cutoff. So with normal CDF, you'd put in the score, and then it would tell you the percentage. But we need something that goes backwards, that kind of undoes this. The way you're going to do this is with something called invnorm. So the way invnorm works, you're going to put in the area that you want here. And then you're going to put in the mean, and then you're going to put in the standard deviation. So with this problem, also invnorm always works from the left. So just like binom CDF and normal CDF, they both work from left to right. So if we want the top 8%, we actually need to plug in the bottom 92% to figure this out. So we are going to do invnorm 0.92. The average is 821, and the standard deviation is 40. And I believe this is 877 with some change. Yeah. So rounded to the nearest cauliflower, or to the nearest gram, 877 grams. So the top 8% of the cauliflowers are 877 or more grams. All right, you guys, that's it for probability. Ask me questions in class, please.